In section 1.2, we will be covering mathematical models, a catalog of essential functions. A mathematical model is a mathematical description, often by means of a function or an equation of a real-world phenomenon, such as the size of a population, the demand for a product, the speed of a falling object, the concentration of a product in a chemical reaction, the life expectancy of a person at birth, or the cost of emission reductions. The purpose of the model is to understand the phenomenon and perhaps to make predictions about future behavior. So if you look at this figure, it illustrates the process of mathematical modeling. You're given a real-world problem, and you formulate the mathematical model, then generate mathematical computations to form mathematical conclusions, and then to interpret the real-world predictions. Now, there are many different types of functions that can be used to model relationships observed in the real world. In what follows, we will discuss the behavior and graphs of these functions and give examples of situations appropriately modeled by such functions. Now, the first one we're discussing is linear models, and we say that y is a linear function of x. We mean that the graph of the function is a line, so we can use the slope-intercept form of the equation of a line to write a formula for the function, which is y equals f of x equals mx plus b, where m is the slope and b is the y-intercept. Now, a characteristic feature of linear functions is that they grow at a constant rate. So, for instance, in this particular figure, it shows a graph of a linear function, y is equal to 3x minus 2, and a table of sample values. And notice that whenever x increases by 0.1, the value of the function also increases by 0.3. So the function f of x increases 3 times as fast as the value of x. Thus the slope of the graph, y equals 3x minus 2, namely 3, can be interpreted as the rate of change of y with respect to x. Now, the first example that's given here is we are interpreting the slope of a linear model. So the first part of this question in part A states that as dry air moves upward, it expands and cools. If the ground temperature is 20 degrees Celsius and the temperature at a height of 1 kilometer is 10 degrees Celsius, express the temperature T in degrees Celsius as a function of the height h in kilometers, assuming that the linear model is appropriate. In part B, we're going to draw the graph of the function in part A and determine what does the slope represent. And then part C, what is the temperature at the height of 2.5 kilometers. So for part A, since we're starting with assuming that t is a linear function of h, then we could write this in the form of t, which is equal to mh plus b, where m is the slope and b is the y-intercept. So from the problem, at ground temperature, the ground temperature noted is that T is equal to 20 degrees. And since it's at ground temperature, then the height would have to be 0. So with that given information, we're able to figure out what is the value of b, meaning the y-intercept. So let's plug it into the equation. So we get 20, which is equal to m times 0 plus b. And therefore, b would equal 20, which would then represent the y-intercept. Now, in part 2, we know that the temperature has a height of 1 kilometer at 10 degrees Celsius. So when T is equal to 10 degrees Celsius, we know that the height is 1 kilometer. And we know that the y-intercept is 20, so we can determine what is the value of the slope. Now, plugging this into our model again here, we have 10, which is equal to m times h, which is 1, plus 20. And so now when we want to solve for m, we would get negative 10, which would represent the slope. And so now what we can do is we can finally then write down what the required linear function would be. And that linear function would be the following. T would equal the slope, which was negative 10, times h plus 20. Now, in order to draw the graph of part B of the function, okay, what we do need to know is the slope and the y-intercept. So from our linear function, we determine that the slope is negative 10 over 1, and the y-intercept is 20. And if we write that as an ordered pair, that would be 0, 20. And if you look here at the graph, if we start at 0 and plot our y-intercept at 0, 20, we can use our slope to go down 10 units to the right 1, down 10 units to the right 1. And therefore what that does is that gives us our line. And then we also need to determine what does the slope represent. Well, the slope, negative 10 degrees Celsius per kilometers, represents the rate of change of temperature with respect to height. Okay, now in part C, we want to determine what is the temperature at height 2.5 kilometers. So we know that h would then represent 2.5, and then we can plug it again into our linear function. So t would equal negative 10 times the height, which is 2.5, plus 20. And so therefore t is going to equal negative 5 degrees Celsius. So what that means is at the height of 2.5, the temperature is going to be negative 5 degrees Celsius. Now, if there is no physical law or principle to help us formulate a model, we construct an empirical model which is based entirely on collected data. We seek a curve that fits the data in the sense that it captures the basic trend of the data points. Now, for example number 2, we are going to investigate a linear regression model. Okay, and table 1 lists the average carbon dioxide level in the atmosphere featured in parts per million at Mauna Loa Observatory from 1980 to 2006. And we're going to use the table in data 1 to find a model for the carbon dioxide level. Okay, now T is going to represent the time in years, and C is going to represent the carbon dioxide level. Now, notice that the data points appear to lie close to a straight line, so it's natural to choose a linear model in this case. But there are many possible lines that approximate these data points. So which one do we actually use? Well, one possibility is that the line is going to pass through the first and the last data points. Okay, so if we wanted to look at the first and the last, so here's the first point and here's the last point. And so therefore we're going to find the slope of that. In order to find the slope of that, we would then just use our slope formula. So we would take y2 and subtract y1. All over x2 minus x1. And so we would approximately get the slope to be 1.6615. Okay? And so now we want to be able to determine what is the model, or what is the equation, not necessarily the model, the equation of those 2 points. So we would use our point slope form, where C minus 338.7 which is equal to the slope, which is 1.6615, times the value of t minus 1980. Now, if we distribute and solve for c, we would get the following equation. C would equal 1.6615t minus 2951.07. And so that represents that equation. And now if you look here, that determines this line. And if you look at those data points, okay, compared to the line, you can see that it passes through the first and the last points, but those other points are still kind of close to it, but not touching it, okay? So this equation just gives us one possible linear model for carbon dioxide level, which is what you see as graphed, okay? Now, our model gives values higher than most of the actual carbon dioxide levels. So a better linear model would be obtained by a procedure in statistics called linear regression. And so in order to do that, you would use a graphing calculator or a computer program to generate a line of best fit that fits the data. So if you look here, a computer or graphing calculator finds regression line by the method of least squares, which is to minimize the sum of squares of the vertical distance between the data points in a line. Okay, and these details are more explained in 11.7. But if you notice here, now look at this line compared to the first graph. This line actually goes through the middle of those points. And they call it the line of best fit because this line best fits the data. So this is the model that would probably best fit and be used for this example. Now, continuing on to example number 3, okay, we want to be able to use a linear model for prediction. Okay, so we're going to use the linear model that we found, which was the last model in the previous example, and that was C, which is equal to 1.62319t minus 2876.20. Okay, and what we want to do is we want to be able to estimate the average of the carbon dioxide level for 1987 and then also predict the level for the year of 2012. And so according to this model, when will the CO2 level exceed 4,000 parts per million? Okay, so for the first part, we know that T is equal to the year 1987. And so we're going to substitute it into our model. And then we'll approximately get 349.08 of carbon dioxide level. Okay. Now, this is an example of interpolation because we've estimated values that were between the observed values, which means that the year 1987 is in between 1980 and 2005. Okay. Now, the second part wants us to estimate what would it be in 2012. And so from here, you can see that the value increases to 389.66. So we're predicting the average carbon dioxide level in the year of 2012 to be 389.7. Now, this is an example of extrapolation because we have predicted the value outside the region of the observations. So consequently, we are far less certain about the accuracy of our prediction. Now, using equation 2, we see that the carbon dioxide level exceeds 4,000 when what? So in order for us to figure that out, we want to set this up using our equation 1.62319t and so in the last part it says when will the CO2 level exceed, meaning that when is it going to be greater than 400 parts per million. And so in order to do that, we'd have to solve for t. So if we add 2876.20 and then divide by 1.6239, we would get t to be greater than or approximately greater than 208.37. So basically what it's saying here is that we would predict that the CO2 level will exceed 400 parts per million by the year of 2018. So this prediction is risky because it involves a time quite remote from our observations. So therefore, CO2 levels to increase rather more rapidly in recent years, so the level might exceed 400 well before 2018. Okay, now then we have another model which is called a polynomial, and a function p is called a polynomial if you have the following. Okay, where n is a non-negative integer and the numbers a0, a1, a subscript 2, a subscript n are constants called the coefficients of the polynomial. The domain of any polynomial is all real numbers. If the leading coefficient does not equal 0, then the degree of the polynomial is n. So for example, the function p of x, which is equal to 2x to the 6th minus x to the 4th plus 2/5 x cubed plus the square root of 2 is a polynomial of degree 6. Okay, now a polynomial of degree 1 is of the form of p of x, which is equal to mx plus b, and so it is a linear function. A polynomial of degree 2 is of the form p of x, which is equal to ax squared plus bx plus c, and is called a quadratic function. Its graph is always a parabola obtained by shifting the parabola y equals ax squared. So as we will see in the next section, the parabola opens upward if the value of a is greater than 0 and downward if a is less than 0. Now a polynomial of degree 3 is of the following form, and it's called a cubic function. So if you look at the figure, in figure 8, it shows the graph of a cubic function in part A and graphs of polynomials of degrees 4 and 5 in parts B and C. And then we'll see later why the graphs have these particular shapes. Okay, now polynomials are commonly used to model various quantities that occur in the natural and social sciences. So when we get to like section 3.8, we'll explain why economists often use a polynomial to represent the cost of producing X units of commodity. So in the following example, we're going to use a quadratic function to model the fall of a ball. Okay, now in this question it's saying here that a ball is dropped from the upper observation deck of the CN Tower, 450 meters above the ground, and its height h above the ground is recorded at 1 second intervals, which you can see is in table 2. We want to find a model to fit the data and use the model to predict the time at which the ball hits the ground. So table 2, you have your time in seconds, and then you have your height, which is in meters. Okay, so what we do is we can draw a scatter plot, which is in figure 9, and observe that a linear model is inappropriate because obviously it won't describe a linear function. But it looks as if the data points might lie on a parabola. So we try a quadratic model instead. Now, again, we can use a graphing calculator or a computer algebra system to obtain the following quadratic model. So because the computer has generated an equation that fits that data well, this is the equation. So we have negative 4.90 t squared plus 0.96 t plus 449.36, which is equal to 0. Okay, and so again, the computer generated this equation to make sure it fits those data points. Okay, now in order for us to solve, we can either use the quadratic formula completing the square. So the quadratic formula might seem like the best way of being able to solve for t here. So we would plug in our given information. So we'd have negative 0.96 plus or minus the square root of 0.96 squared minus 4 times negative 4.90 times 449.36, and then divide that by 2 times negative 4.90. And so then we are only going to be dealing with a positive root. And so we end up with two values. One was negative and one is positive, but we're going to use the positive value, which ends up being 9.67. Okay? And so what that means is that's the time, 9.67 seconds. So we predict the ball will hit the ground after about 9.67 seconds. Okay, now we also have what we call our power functions. And a function of the form f of x equals x to the a, where a is constant, is called a power function. And we're going to consider the following cases. Okay, so when the first case is that when a is equal to n, and that's when n is a positive integer. So the graphs of the function for when it's equal to x to the n, for n is equal to 1 all the way through 5, are shown in figure 11. Okay, they are polynomials with only one term. And we already know the shape of the graphs y equals x, which is a line to the origin with slope 1, and y equals x squared is a parabola. Now, the general shape of the graph of fx equal to x to the n depends on whether n is even or odd. So if n is even, then f of x equals x to the n is an even function. And its graph is similar to the parabola of y equals x squared. If n is odd, then f of x, which is equal to x to the n, is an odd function. And its graph is similar to that of y equals x cubed, which is the cubic function. Now, if you notice, okay, in the next figure, as n increases, the graph of y equals x to the n becomes flatter near 0 and steeper when the absolute value of x is greater than or equal to 1. Okay, so, sorry, let me go back to here. That's a little further down. Okay, so again, I want to restate this. Notice that from figure 12, you can see down here below that as n increases, meaning the graph of y equals x to the n becomes flatter near 0 and steeper when the absolute value of x is greater than or equal to 1. So if x is small, then x squared is smaller, x cubed is even smaller, x to the fourth is smaller still, and so on. Okay, our next is that when a is equal to 1 over n, where n is a positive integer. Okay, the function f of x equals x to the 1 over n, or it's the same as nth root of x is the root function. So for n is equal to 2 is the square root function, okay, of f of x equals the square root of x, whose domain is including 0 all the way to infinity, and whose graph is the upper half of the parabola x equals y squared. Now, if you look at the first figure, that would give you the first figure for the first scenario. Now, for other even values of n, the graph of the nth root of x is similar to that of the graph of y equals the square root of x. Now, for when n is equal to 3, we have the cube root function, meaning the third root of x, whose domain is all real numbers. And so recall that every real number has a cube root, and whose graph is then shown in figure B. So the graph of the following function when you have the root of x for when n is odd is going to be similar to that of the cube root of x. Our third scenario is when a is equal to -1, and this is called the reciprocal function. So f of x is equal to x is equal to f of x is equal to x to the -1 is equal to 1 over x is shown in the figure. Its graph has the equation y equals 1 over x, or x times y equals 1, and it is a hyperbola with the coordinate axis as its asymptotes. This function arises in physics and chemistry in connection with Boyle's law, which says that when temperature is constant, the volume V of a gas is inversely proportional to the pressure P. So V is equal to C over P, and you will see that if you're taking physics. Okay, C is the constant. Now, the graph of V is a function P, which you can see in figure 15, has the same general shape as the right half of the original figure in figure 14. Okay, then we also have what we call our rational functions. And a rational function f is a ratio of two polynomials, where p and q are polynomials. The domain consists of all the values of x such that the denominator cannot equal 0. A simple example of a rational function is the function f of x, which is equal to 1 over x, whose domain is x such that x cannot equal 0. This is the reciprocal function graphed in figure 14. Now, the function f of x, which is equal to 2x to the fourth minus x squared plus 1 over x squared minus 4, is what's graphed in figure 16. It's a rational function with the domain where x cannot equal 2 plus 1 or 2. And you can see that figure in figure 16. So therefore, it generates two vertical asymptotes, one at x is equal to -2 and the other one at x is equal to 2. Okay, then we have algebraic functions. So a function f is called an algebraic function if it can be constructed using algebraic operations such as addition, subtraction, multiplication, division, and taking roots. Starting with polynomials, any rational function is automatically an algebraic function. So here are some examples that you can see. Now, when we sketch algebraic functions in Chapter 4, we will see that their graphs can assume a variety of shapes, and you can see that from Figure 17. Now, an example of an algebraic function occurs in the theory of relativity. So the mass of a particle with the velocity v is the following, where m is equal to f of v, which is equal to m, meaning the slope there, the initial, divided by the square root of 1 minus v squared over c squared. Okay, so therefore, the initial mass is the rest mass of the particle, and c is equal to 3.0 times 10 to the 5th kilometers per second is the speed of light in a vacuum. Then we also have trigonometric functions. So trigonometry and trigonometric functions are reviewed on the reference page 2 and also in the appendix C. So in calculus, the convention is that radian measure is always used except when otherwise indicated. So for example, when we use the function f of x, which is equal to the sine of x, it is understood that sine of x means the sine of the angle whose radian measure is x. Thus, the graphs of the sine and cosine functions are also shown here in figure 18. So you have your graph of the sine of x and the graph of the cosine of x. Now going back to the trigonometric functions, I do want to point out something here. Now notice that for both the sine and the cosine functions, okay, the domain is negative infinity to positive infinity. Okay, and the range for both of them goes from -1 and 1 inclusive. So what that means is that for all values of x, we can say that the sine of x is going to be in between -1 and 1. And the cosine of x is also going to be in between -1 and 1. Okay, in terms of the absolute value, the absolute value of sine of x is less than or equal to 1. And the absolute value of cosine of x is also less than or equal to 1. And then the zeros of the sine function occur at integer multiples of pi. So what that means is you would say that sine of x is equal to 0 when x equals n times pi and n is an integer. Okay, so an important property of the sine and cosine functions is that they are periodic functions and have period of 2 pi. So let me make note of that here. So an important property, and I'm going to go ahead and put an asterisk down here, which I think is very important, is that sine and cosine functions are periodic and have a period of 2 pi. So what this means is for all values of x, the sine of x plus 2 pi is equal to the sine of x, and the cosine of x plus 2 pi is equal to the cosine of x. Okay, now the periodic nature of these functions makes them suitable for modeling repetitive phenomena such as tides, vibrating springs, and sound waves. So for instance, in example 4 in section 1.3, we will see that a reasonable model for the number of hours of daylight in Philadelphia T days after January 1st is given by the following function. Okay, then we also have the tangent function, which is related to the sine and the cosine functions by the equation tangent of x is equal to sine of x over the cosine of x. And its graph is shown in the figure 19. It is undefined whenever the cosine of x is equal to 0, that is, when x is equal to plus or minus pi over 2, plus or minus 3 pi over 2, and so on. Its range is negative infinity to infinity, and notice the tangent function has a period of pi. So therefore, for all of x, the tangent of x plus pi is equal to tangent of x. Okay, and the remaining three trigonometric functions, cosecant, secant, and cotangent, are the reciprocals of the sine, cosine, and tangent functions, and their graphs are also shown in Appendix C. Again, these three items you definitely want to make note. Okay, now we have exponential functions. The exponential functions are the functions of the form f of x is equal to a to the x, where the base a is a positive constant. So the graphs of y equals 2 to the x and y equals 0.5 to the x are shown in the figure. And in both cases, the domain is negative infinity to infinity, and the range is 0 to infinity. Exponential functions will be studied more in detail in section 1.5, and we will see that they are useful for modeling many natural phenomena, such as a population growth and radioactive decay. And then we also have logarithmic functions. And a logarithmic function, f of x, which is equal to the log of base ax, where the base a is a positive constant, are the inverse functions of the exponential functions. They will be studied in section 1.6, and then figure 221 shows the graphs of 4 logarithmic functions with various bases. In each case, the domain is 0 to infinity, and the range is negative infinity to infinity. And you can see that the function increases slowly when x is greater than 1. Okay, now in example number 5, we want to classify the following functions as one type of functions that we have discussed. So for the first one, f of x, which is equal to x to the 5, this is a what? An exponential function. And the key thing to notice here is that x is the exponent. Okay? For g of x, for part B, g of x is equal to x to the 5th. This is a power function. And if you notice, x is in the base. So we would also consider that the polynomial has a degree of 5. In part C, this is an algebraic function. And then in part D, this is a polynomial with a degree of 5. A degree of 4. And that concludes section 1.2.